My name is Perlroth, and I'm presenting the paper Maximizing Revenue in the Presence of Intermediaries. This is a joint work with Gagan Aggarwal, Kshipra Bhawalkar, and Guruganesh. We're part of the market algorithm teams at Google Research. A common feature that we observe when we think about auction design is that most of the time, we assume that the buyers interested in getting the goods that are sold in the auction are the one actually bidding in the auction. However, in many markets, this is not actually the case. There are intermediaries who are the one representing buyers, and those intermediaries are the one bidding in the auction. For example, in that auction world, an advertiser who wants to purchase an impression from the publisher is actually represented by a chain of intermediation, the ad agency, and also the DSP, the demand side platform, who are the ones bidding on behalf of the advertiser in that exchange. So what could change in auction design when those intermediaries are the one bidding the auction? Consider the following example. There are three buyers, these little mouses, who want to purchase this cheese that is sold by the seller through, to make analysis simpler, a truthful auction, a second price auction. Since the auction is truthful, everyone reports the value, and therefore the high valuation buyer, the mouse in the left-hand side, will get the item and is going to pay the second highest bid, 0.8. Thus, the revenue of the seller, in this case without intermediaries, is 0.8. Now, consider the intermediary, this little cat, who is representing the buyer of the left-hand side, the high valuation buyer. The intermediary says it's going to charge a markup fee of $0.3 as a broker whenever he purchases a cheese on behalf of the buyer he represents. So, given the situation, the maximum bid that the high valuation buyer could actually bid in the auction is no more than 0.7, since the buyer needs to pay at least $0.3 as the markup fee to the intermediary. Because of that, the 0.8 bid of the second highest valuation buyer is going to win the auction, and therefore 0.7 is going to be the second highest bid, which is also the seller's revenue. So we see from this exercise that because there is an intermediary who is charging a markup fee, the seller's revenue decreases, and there is a suboptimal allocation of the good. Now consider the following example in which now not only the high valuation buyer is represented by the intermediary, but also the second highest valuation buyer is also represented by the same intermediary. In this case, the intermediary is going to submit only one bid to the final auction, since there's only one item there. And therefore, the second highest bid in the auction is going to be the third highest valuation buyer, 0.4. Thus, the 0.7 bid of the high valuation buyer is going to win the auction, but is going to be end up paying 0.4 in the auction. So therefore, the seller's revenue now decreases even more to 0.4. So what happened here? So we see is that because the intermediary is representing multiple buyers, he enables those buyers to collude to decrease the price pressure in the final auction. Now, to see this example to an even more extreme case, let's assume, or let's consider the case where all three buyers are represented by an intermediary. In this extreme situation, there's no competition in the final auction, as the intermediary is going to submit only one bid. So in this extreme case, the seller's revenue is going to be zero. It's going to sell the cheese by a very tiny amount of price. So what we see from this example is that we think about auction design is very important to take into account whether there are intermediaries in the auction or not. So the previous example showed that intermediaries are negatively impacting sellers' revenue. Is this always the case? And the answer is no. To see this, consider the following example where now the seller owns multiple goods, two cheeses, and they are the same buyers. Each buyer wants to buy only one cheese. So we stick with the same exercise of thinking about truthful auctions. In this case, the VCT auction is going to be a third price auction. Thus, each item is going to be sold by the third highest bid, and since the auction is truthful, it's going to be 0.5, which means that each cheese is sold at 0.5 to the two highest valuation buyers, and the total revenue is 1. So now what happens when there is an intermediary? Well, if there is an intermediary and the seller is aware about the intermediation, he may want to choose a bundling price to sell the two goods together at the price of 2.8. Since the two highest valuation buyers, the sum of their value is 3.5, and the markup price to buy the two goods that they will have to pay 0.6 in total, and the bundling price 2.8, the total value, which is 3.5 versus the value of the bundling 2.8 and the intermediation 0.6, makes that it's worth to make the transaction, and therefore the intermediary will purchase the goods on behalf of these two buyers. Thus, the total revenue in this situation was 2.8 because there is an intermediary, while in the previous case 1.0. So what happened here is that because the intermediary is representing multiple buyers, the seller can start using strategies of bundling, which are known to be profitable and very useful when we're thinking about multiple goods, that those strategies would not be able to be used in the case that there's no intermediaries in the auction. So this may lead to think that it will be a good strategy for the seller to set the bundling price. Suppose he actually believes that the market is as we described, where one intermediary represents all the buyers and sets this bundling price. But he was wrong. And actually, there's no intermediary in the auction. Oh, in this case, he's going to be forcing each buyer to buy two goods, although they care only about one, at a very high price. In particular, given the valuations that we observed in the example, no buyer will be able to purchase the goods. Thus, the revenue of the seller is zero, since he doesn't sell any of the goods. What we see from this example is that when we think about auction designs and intermediaries, we also have to be careful about the implications if the demand structure changes. And therefore, it will be important to have an auction system which is going to be robust to the demand structure. Given this motivation, let me present you the main model that we study in this paper. We're going to first assume that the seller owns k identical items, and later discuss an extension when we discuss heterogeneous items. There are going to be n unit demand buyers with as valuations IID drawn from the Sydney distribution F. The introduction intermediaries are going to be summarized by what we call the demand structure, M pi, where M are the number of intermediaries, and pi L represents the buyers that intermediary L is representing in the auction. For instance, in the classic example of competition, this would represent that each intermediary is the buyer, and therefore he only represents herself. Also, another classical canonical instance that have been studied is the case where one intermediary represents all the buyers, the monopsony case. In that situation, there's going to be only one intermediary who's going to be representing all the buyers. So the key challenge that we want to also discuss in this paper and we elaborate is about how to summarize all the interactions and decisions that happen downstream market between the buyers and intermediaries. And this is going to be summarized by the utility function UL of the intermediary. So we have two main interactions that we have in mind. The first one is the surplus sharing intermediary. In this situation, the intermediary wants to maximize the sum of the utility of the buyers he or she represents. And the second instance that has been widely studied is the case where the intermediary actually wants to maximize its own profit, and therefore he acts as a profit maximizer broker. So with these two canonical examples, we want to develop an abstract utility function that would include as particular instances these two cases. So at the end, we're going to be assuming that our utility function will have three main properties. It's going to satisfy individual rationality. That means that if an intermediary does not receive an item, he gets a payoff of 0. The second property that we're going to impose is that the intermediary does not create value given the utility function, which means that the utility function of the buyer cannot be greater for any allocation to the value he could generate via the buyers he or she represents. And the third property, which is a bit more subtle, that has more nuances, is the following, which we call buyer disconnectability. Assume that the seller sets all the prices for all the items at the price of R. So if there will not be intermediary, any buyer with value greater than R will actually try to purchase the item. With intermediation, that cannot be necessarily the case, but we're going to be assuming that it will happen at least with probability tau L. The idea behind that is that tau L captures the level of double marginalization. For instance, in the case of surplus sharing intermediary, since the intermediary wants to maximize the value of the buyers, he will always want to purchase if a buyer wants to purchase. Thus, tau L is 1. However, in the case of double marginalization, when the intermediary is a profit maximizer, he will start setting markup fees. And therefore, as we saw in the previous examples, there are sometimes where a buyer would like to purchase the good, but given the fee, it's not going to be worth for him. So therefore, the probability of trade will not be 1. However, when distributions have nice properties, for instance, has a monotone hazard rate, this probability cannot be so small. In particular, for a mature distribution, tau L is actually equals to 1 over E. So with that in mind, what's our goal? We want to design an auction so that the seller maximizes his revenue. So we have a seminal result by Kai et al. Who shows that if we give you as granted the demand structure and the intermediaries, there is an algorithm which can tell us what is the optimal revenue that the seller should implement, the optimal revenue mechanism that the seller should implement to maximize the revenue. However, in most of the cases, this mechanism is actually quite complex. And furthermore, and this is critical for our purposes, is very sensitive to the demand structure and also the intermediaries utility functions, meaning the downstream interaction that happens between the intermediaries and the buyers. So with that in mind, what we're going to be our goal of this paper is to design a simple mechanism, but with the good guarantees for all kind of intermediaries and for all demand structures that may arise in the downstream market. So to have good revenue guarantees, a key technical aspect a key element that we develop in the paper is to provide a good benchmark to compare revenue. And our benchmark corresponds to the welfare. This corresponds to the highest valuation the seller could have under any demand structure, which is just to charge the highest valuation to the k highest bidders, k highest buyers that are below that are present in the market. The nice property of the welfare as a benchmark is that this is independent of the demand structure, and of course, by definition, its revenue for any demand structure cannot be greater than the welfare. So our goal will be to find a mechanism such that for any demand structures, any payoff that the intermediaries could have, given the properties that we previously described, would satisfy that it will have a constant factor compared to the welfare. And because of that, it will mean that it will have a constant factor to the optimal revenue had we have implemented the revenue maximizing mechanism given the demand structures and the particular utility functions of the intermediaries. So the first point that we realize in this work is that we cannot assume that the distribution F is too general. For instance, if we think about the equal revenue distribution, which has nice properties in the sense that it is regular according to the Majorstonian sense, that its virtual evaluation phi f is non-decreasing, is such that the welfare is infinity while the revenue is 1. So therefore, we cannot use in this case, for instance, welfare as a benchmark because it's too high to compete with that. So what we do is to restrict a bit the class of distribution to what we call the lambda regular distributions. So lambda regular takes the virtual evaluation from Meyerson and adds a lambda factor to the first element. And we're going to impose a stronger monotonicity, that is that lambda b has minus the inverse of the hazard rate has to be increasing. This is a subset of regular distributions. And the nice properties of lambda regular is that, well, in the paper we show that it's close under maximum. That is that if the distribution f is lambda regular, the maximum of f of n distributions is also lambda regular. And also that the probability that the value exceeds its expected value is a constant factor that depends on lambda. And this term 1 minus lambda over 1 over lambda is going to appear in our analysis quite often. So we summarize by the C lambda. And a second result we show is that the previous tau for the profit maximizer bidder, the probability of trade that we saw that for MHR is 1 over E, actually can be generalized for lambda regular, and the probability of trade, even he does markup fees to maximize revenue as an intermediary, to maximize profit as an intermediary, the probability cannot be smaller than this value C lambda. So without this assumption of distribution, let me present you our main mechanism, which is the intermediate proof mechanism. And the idea is the following. Let's divide in K groups the buyers. So they're going to be S buyer in each of the groups. And we're going to pick the highest of those buyers, compute the expected value, and charge that as the price. And we're going to sell this, we're going to sell each item at that price. And the mechanism is such that if there is excess demand, meaning more intermediaries want to buy the goods than the amount of goods, we're going to be randomly allocated among the interested bidders. So what's our main result? Is that we show that if the distribution is lambda regular, for any demand structure, and any payoffs satisfying buyer disconnectivity with factor tau, we're going to have that the revenue that we're going to obtain with this IP mechanism, this intermediate proof mechanism, is a constant factor of the welfare. And the constant factor it can be breakdown as follows. So the first element tau comes because the rents that intermediate may be extracting, and therefore it decreased rate. The second factor, C lambda, comes because of the gap between the optimal revenue and the welfare, even in the single bidder's case. This C lambda is in terms what's the probability, as we saw before, that the highest valuation buyer in each of those groups are going to oversee the expected value that we are setting as a price. The 1/2 value that appears here comes from some technical assumption, technical analysis for the case where the groups are actually the division n divided by k is not an integer. And the last term in the constant factor approximation is a loss from our order statistics lemma we show in the paper. The lemma shows that the price we set for each item is actually comparable to the welfare. But it has a second interpretation. It says that if we restrict a seller to allocate each of the k goods to the bucket of size n divided by k, the welfare of this restrictive allocation is comparable with this constant factor to the welfare if it will not be constrained, and he can allocate freely the k goods to the end buyers. So with this intuition in mind, that's the last element of the constant factor that we use to compare to welfare. Now let me show you our extension where we discuss now the setting with heterogeneous items. So we're going to be considering that each item has a weight eta I. This is a common assumption, especially in display advertisement when there are multiple slots in the auction. So buyer's I value for the item is going to be separable. It's going to be on his private valuation times the weight that the good J has, eta J. Thus, in this case, the welfare, the maximum revenue the seller could possibly have under any potential allocation, is going to be allocating the highest good to the high valuation buyer, the second highest good to the second highest valuation buyer, and so on. So even though this mechanism sign problem, once we know the demand structure and the intermediaries utility function is solved by Kai et al. as the previous example with the homogeneous setting, it is unknown to find a mechanism which have these properties to be robust to the demand structure. So here we also show that we provide an intermediary proof mechanism which will satisfy these robust properties. And the mechanism is as follows. We're gonna sell an item at the price Rj, which is given by this recursion. And the idea of this recursion has a flavor close to the GSP, and the pricing are set so that if we are able to sell each good at those prices, we're gonna be competitive against welfare. So the question is, what's the probability that we're gonna be selling each good? So we show actually that if each buyer's valuation is between an interval of uj and uj minus 1, where uj is given, as you can see in the slide, then we know for sure that if the value is in this particular interval, the buyer I wants to purchase an item j. So the question is, what's the probability that the buyer's valuation is going to be in that interval? And what's the probability that we're going to have k buyers in each of those intervals, at least, to have a constant factor approximation, meaning that to have with constant probability trade in each of the items. So to tackle that key issue, we discuss in the paper a new technique using a convex program and duality techniques, and we're able to show that with constant probability, the items are going to be allocated. Each of the items are going to be allocated to the first buyer, the highest item, and so on. So what's the mechanism with this pricing? The mechanism is going to be as follows. So we're going to be offering to each intermediary a menu of all the goods. Then the intermediary can purchase any of the goods. Then we're going to pick the second intermediary, which is going to be randomly chosen, and offering the remaining goods until we go until the end of until the last intermediary. So using these convex programs with constant priority, all the goods are going to be sold. And this actually turns into this 1 minus exponential that depends on lambda expression. And therefore, going to be a constant factor of the welfare for any demand structure, for any utility function, that for any demand structure and for any distribution that is lambda regular, so long as the intermediaries are surplus sharing intermediaries. It remains an open question if for the case where intermediaries, for instance, are profit maximizers. So let me, with that in mind, finish this talk with open questions that are remaining unanswered in this work. First, a key assumption that we do is to restrict to lambda regular distributions. And as we show that if we think about regular distributions, our technique that comparing to welfare can no longer apply. And furthermore, actually, we show that for regular distribution, a uniform single item pricing mechanism, even for a homogeneous case, as we saw worked for lambda regular, does not work in this general setting for regular distributions. So there is an open question of whether exists a demand, a robust mechanism, robust intermediaries, robust demand structure, and if that exists, it will have to be more complex. And the second question that we don't discuss in the paper, and we think is an interesting venue for future research, is about extending our analysis beyond the IID framework. What happened about intermediary proof mechanism where buyers do not have the same valuations, and therefore we believe that it would require some personalized pricing in order to obtain good revenue guarantees among all different demand structures. Thanks so much for listening to my talk, and look forward to see you in the conference. Thanks so much.